I'm going to prove Euler's formula, but I'm going to do it without using any power series. I'm just going to use integrals. So you can follow this video even if you don't know Calculus 2. This is all Calculus 1 topics. So I have a couple of integrals up on the screen here. Let's take a look at the one on the left. We're integrating 1 over t squared minus 1. In order to do that, we would have to use a partial fraction decomposition. We'd factor the denominator, so we'd say it's the integral, and we have the 1 on the top. And we know that t squared minus 1 can be factored to t minus 1 and t plus 1. And then we would do a partial fraction decomposition. So we'd say, okay, this equals the integral. And we could break this fraction apart. We'd have two fractions added together. One of them would have denominator t minus 1, and the other would have denominator t plus 1. And we'd get just some numbers to go on the top here, and we'd be able to integrate that nicely. I'm not actually going to do it because it's not relevant to what we're going to do. Now let's take a look at this integral on the right here. We're integrating 1 over t squared plus 1. Now this time we can't factor it, at least not with real numbers. We'll get to the factoring with complex numbers in a moment. But fortunately, we know that we can just put down the answer for this as being the inverse tangent of t, and of course plus a constant. But I got to thinking, what would happen if we factored this? T squared plus 1 cannot be factored using real numbers, but I could think of it as t squared minus negative 1, which is the same as t squared minus, and negative 1 is I squared. And now we have a difference of squares. We could factor this as t minus I times t plus I. So I got to thinking, what would happen if we did this integral two different ways? First way is just realize that we get the inverse tangent, and the second way by factoring. So let's go ahead and take a look at that. Let's get a blank screen here. All right, so let's write this down again. So we're going to take a look at the integral of 1 over t squared plus 1 dt. And I'm just going to go ahead and set it equal to itself. So I'll just write it down again. Integral of 1 over t squared plus 1 dt. Now, this is not entirely true because we're dealing with indefinite integrals. We have an extra constant in here. So I'm actually going to fix that, and I'm going to make these definite integrals. I'm going to make them go from 0 to x. So now these are just functions of x, no arbitrary constants. T is like a dummy variable. So now we have one function of x equals to itself. So this should be good. So we're going to do this integral two different ways. So let me just write this down again. Integral 0 to x of 1 over t squared plus 1 dt equals. All right, this one we're going to use the inverse tangent for. On the right-hand side, we have integral 0 to x. I'm going to factor the denominator. So we know that t squared plus 1 can be factored to t minus I times t plus I. And now we still have the 1 on the top. Okay, let me just write this down one more time. Integral 0 to x, 1 over t squared plus 1 dt equals integral 0 to x. All right, now let's do the partial fraction decomposition. So we know we're going to have two fractions added together, and we know that the denominator of the first fraction is going to be t minus I, and the denominator of the second fraction is going to be t plus I. All right, now how can we figure out what constants we need on the top? We can use the cover-up method. So to get the number we need on top here, we'll go back to this fraction, and we'll cover up this denominator. Although actually first I should set this denominator equal to 0. If we set this denominator equal to 0, that means that t minus I equals 0. That means t equals I. So now I'll cover this up, and I'll plug t equals I into the rest of this here. And you'll see that we get 1 over I plus I. In other words, 1 over 2I. So that's going to be my numerator for this one. 1 over 2I. All right, now we'll do the same thing here. We'll set this denominator equal to 0. That means that t plus I equals 0. That means t equals negative I. We'll cover it up, and we'll plug t equals negative I into the rest here. And when we do that, we'll get 1 over negative I minus I. In other words, negative 1 over 2I. So this numerator is going to be negative 1 over 2I. Okay, now let's actually integrate. Let me go ahead and get some more space here so we can do this. Okay, So now, on the left-hand side, we're going to use inverse tangent. So we know that integrating 1 over t squared plus 1, we just get the inverse tangent of t. And again, this was a definite integral, so we're going to evaluate this from 0 to x. And this is equal to, all right, on this side, integrating 1 over 2i, that's like a constant multiple, so I'll just keep it, 1 over 2i. And because we have a nice linear denominator here, it's just going to be the natural log of that denominator. Please do not use an absolute value, right? No absolute value. We're already dealing with complex numbers. If you use an absolute value here, that will screw everything up. All right, so that was the integral for the first term. And if you want to check, you can differentiate this, and you will get that. All right, now for the second term, similarly, this time our numerator is negative 1 over 2i. That's like our constant multiple. And then we're, again, just going to get the natural log of the denominator, t plus I. And definite integral, so we're going to take this whole thing, and we're going to evaluate it from 0 to x. All right, let's do this. On the left-hand side, let's evaluate. So we'll plug in x. We get inverse tangent of x. Let me write that a little bit better there. Minus. Now we have to plug in 0. So we'll have the inverse tangent of 0 equals. Okay, let's plug in x here. So in other words, we're just going to replace all the t's with x's. So we're going to get 1 over 2i natural log x minus I minus 1 over 2i natural log x plus I. All right, so that's what I got when I plugged in x. Now I have to subtract, and now I have to plug in 0. So we're going to have 1 over 2i natural log 0 minus I is negative I. Okay, and then we have 1 over 2i natural log of 0 plus I, which is just I. Okay, now let's simplify. On the left-hand side, we have the inverse tangent of 0. Well, that's just 0, so we just have the inverse tangent of x equals. All right, these two terms, we can combine them. We have the 1 over 2i in the front, and we can factor that out. So we have natural log of x minus I, and I'm going to factor out that 1 over 2i. So this is going to become minus natural log of x plus I. All right, and then over here, I'm going to do the same. We have the 1 over 2i. Factor it out, we get natural log of negative I, and this is, I'm still a minus, the natural log of I. All right, now let's start combining things. So we have inverse tangent of x equals 1 over 2i. And by the way, I can factor that out again from each of these terms, because we have it here and here. All right, but let's do this individually here. So we have a difference of natural logs, and by a log property, I can write that as the log of a quotient. So this is going to become the natural log of x minus I over x plus I. Again, that's just a log property. And then from here, so that was this term, and we're going to have minus, and I already factored out the 1 over 2i to the front here. We're going to have natural log, and again, we can combine them. We have a difference of natural log, so we're going to get the natural log of negative I over I. Okay, let's move on. Let me drag the screen down so we have some more space. Let me grab the red pen here. So I have this 1 over 2i right here. Go away, please. Thank you. I'm going to multiply both sides by that so that we can get rid of it. So we're going to multiply both sides by 2i. So the 2i's will cancel out on that side. On the left-hand side, we're multiplying by 2i, so we'll have 2i inverse tangent of x equals. All right, so we got rid of this by multiplying by 2i. Now let's take a look at this right here. So we have the natural log of x minus I over x plus I minus the natural log, well, negative I over I is just negative 1. Again, this is why we don't use absolute value here, because otherwise you'd just be taking the natural log of 1, and we don't want to do that. All All right, so this is 2I inverse tangent of x equals, all right, we have a difference of natural logs here, so again, we can combine the natural logs by that log property. So we have the natural log of x minus I over x plus I. And then we have to divide this inside by -1. So dividing by -1 is the same as multiplying by -1. Let me just put down a negative right here. Okay, and let me just make this look a little nicer here. 2I inverse tangent of x equals natural log. So I'll just distribute the negative here. The opposite of x minus I is just I minus x. And I'll just reorder the terms on the bottom. X plus I is the same as I plus x. Okay, now I'm going to get rid of the natural log. So I'm going to exponentiate both sides. So I'll do e to this power and e to that power. And we'll have e to the 2I inverse tangent of x equals, of course, e and natural log cancel each other out, I minus x over I plus x. Now, we want to get a formula in the end for e to the I theta. So let me first of all get rid of this 2. So we have the 2 in the exponent, so to get rid of it, we can take the square root on both sides. So square root here, square root here. But because we're taking the square root on both sides, we should put down a plus or minus on one side. All right, so here you'll see that the square root and the second power will just cancel each other out, and we'll be left with e to the I inverse tangent of x equals plus or minus square root of I minus x over I plus x. Now, I mentioned we want a formula for e to the I theta. Well, the inverse tangent of x, inverse trig functions represent angles. So what I'm going to do is I'm just going to choose theta to be an angle, and I'm going to let theta equal the inverse tangent of x. And I'm going to go ahead and plug that into both sides of this formula. So I'll say e to the I, and then the inverse tangent of x is theta, equals plus or minus square root I minus x. Now x, if you go ahead and take the tangent on both sides here, you'll get x is the tangent of theta. So we have I minus tangent theta over I plus tangent theta. Okay. Now we're just going to do some trig work here. I mean, we do have a formula now, pretty much. We have a formula for e to the I theta, but I'm just going to simplify it a little bit. So we have e to the I theta equals plus or minus square root. I'm going to go ahead and multiply both sides by the conjugate of the denominator. Well, not both sides. I'm going to multiply the top and bottom is what I meant to say. So I'll multiply by the conjugate, I minus tangent theta, on the top and the bottom. I plus tangent. Well, no, I have to multiply by the same thing on top and bottom, so that should be a minus. I minus tangent theta. And let me just extend the square root sign to make that clear that we're still in the square root. All right, on the top, we have I minus tangent theta times itself. So in other words, we have I minus tangent theta squared. On the bottom, again, this is the factorization for difference of squares. So we're going to get I squared minus tangent squared theta. This is e to the I theta equals plus or minus. Now, let me put down the fraction bar first, and I'll take the square root on the top and the square root on the bottom. Because when I take the square root on the top, we have the square right here. Those will cancel out. So we just have on the top I minus tangent theta. And yes, I canceled out square root and the square, so I should put down a plus or minus, but we have one in the front already, so we don't need to put down another one. Now, don't forget on the bottom, we are still taking the square root. We have I squared, which is -1, minus tangent squared theta. Let me go ahead and factor out that -1 from both terms, so we'll have the negative in the front, and then I'll just make that positive. Again, I just factored out the negative from both terms. Okay. So we have e to the I theta equals plus or minus I minus tangent theta tangent theta, like that, over, okay, the square root of -1, so this is like a factor of -1 inside that square root. That's going to give us an I, and the square root of I of 1 plus tangent squared theta. Well, 1 plus tangent squared theta by a trig identity is the same as secant squared theta. And now again, we can cancel out the square root and the square, and we don't have to put down plus or minus because we have one in the front already. Okay? E to the I theta equals, let me write this better, e to the I theta equals plus or minus I minus tangent theta over I secant theta. All right, now let's go ahead and do some work here. I'm going to multiply the top and bottom by I just to get rid of it. In fact, maybe I'll multiply by -I. That'll work out a bit more nicely, even though the negative doesn't really matter because we already have the plus or minus in the front. E to the I theta equals plus or minus. All right, now on the bottom, the reason I multiply by -I is that I times I is -1, so I times -I is just 1. So these can actually just be canceled out. And now we just have secant theta on the bottom. On the top, again, I times -I is 1. And then we have minus times a minus becomes a plus I tangent theta. Okay, now let's just go ahead and simplify this. E to the I theta equals plus or minus 1 over secant theta is cosine theta by definition, because secant is the reciprocal of cosine. 1 over secant is cosine theta plus I. All right, now we have tangent theta over secant theta. Tangent is sine over cosine. Secant is 1 over cosine, but because it's already on the bottom, dividing by secant, again, you're just multiplying by cosine. And I should put down these thetas here. These will cancel out, and we see that tangent theta over secant theta is the same as sine theta. All right, and now we're pretty much done. We have e to the I theta equals plus or minus cosine theta plus I sine theta. Which is it, though? You know, if I have a formula for e to the I theta, if I pick a value of theta, I just want to get one thing. I don't want to have a plus or minus. So let's pick a test value, and the easiest test value is theta equals 0. So I'm going to take theta equals 0. I'm going to plug that in on both sides. So I have e to the I times 0 equals plus or minus cosine of 0 plus I sine of 0. Okay? All right. This is e to the 0, which is 1, equals plus or minus cosine of theta is 0. Sorry. Cosine of 0 is 1 plus, all right, sine of 0 is 0, so this just becomes 0. So we have 1 equals plus or minus 1. Now it's pretty clear from here that we have to take the positive version, because 1 equals 1, not -1. That means we have to take the positive version right here as well for this to work. So in the end, we have, if I could get my black pen out here again, e to the I theta equals positive cosine theta plus I sine theta. And there we have it. Euler's formula proved without using power series.